So hello and thanks everybody. Welcome to the summer school. Hope everybody's doing well. Okay, so I'm going to build on some of the things that Martin talked about. The main goals of the talk, are to compute the cohomology of the DJ space that Martin talked about, which is, you can also write that as CP infinity, comma, point upper K as a polyhedral product. And the other one is to compute essentially the cochains of, well, what would be ZK, or the other notation for that would be D2S1 upper K, that as a differential graded algebra, as a DGA. So that's a differential graded algebra. Of course, C star has the product structure. So this is like, if you just take differential and graded together, that would be a chain complex. If you only have a differential graded object, that's a chain complex. And then algebra is you also have a multiplication. And in this case, it's the cup product. Okay, so that's basically the outline. And this will, for the second part, I'll just use a method of Matthias Franz. And basically, the other method is using homotopy colimits and kind of considering these things by adding one simplex at a time. Okay, so I'll just go over, just for notation, some of the things that Martin said quickly. So you have K as a simplicial complex. And it's on these vertices M, right? So M is just the numbers from 1 to M. And then, right, so a simplex can be any subset of M. So, if you have an element of that, then sigma would be a subset of M. And one thing that's important that Martin didn't mention is that sometimes simplicial complexes can be non-empty subsets, but in our case, we include the empty set. That's important. So the empty set for our simplicial complexes is always in the simplicial complex. Okay, so if you have, like here, you would have M equals 3, and then you would have, again, just like Martin did, you can draw a picture like this for a simplicial complex. This would be K. And then that would represent, this K would be equal to, well, what are the subsets there? You have the empty set, you have 1, you have 2, you have 1, 2, and you have 3. Now, it's those things. Now, I should probably put, these are individual subsets. So I can go like that, but sometimes I'll not add that to the notation just for simplicity, just so I don't have to write so much. Okay, so that's a simplicial complex, and that's an example. The other one that we're interested in is, well, if you have sigma is an element of K, so that means that sigma is a subset of M. And then you can write, well, you can consider 2 to the sigma, and that's like, you want to consider this as a simplicial complex in itself. It's all the subsets of sigma as a simplicial complex. And then you'll have what's called like the boundary of sigma, essentially, which would be equal to 2 to the sigma, all the subsets of sigma, but you take away the particular subset sigma. And again, for simplicity, this will be like misuse of notation. We'll also denote this as sigma. Okay, so this is also denoted as sigma. It's abusive, but we'll do that. Okay, so you have the simple case of like 1, 2, and this one, 1, 2, so that would be sigma, and that would be d sigma. That's an example. I guess I'll go like this. Okay, so what's next? Oh, right. So now we want to kind of consider this. We want to take colimits and so on. So we can consider K as a post set. A post set, so it's a partially ordered set. So we have, if we would have that sigma is considered less than or equal to tau, just in the standard way, if sigma is a subset of tau, and then associate to that, we can associate a post set category. Post set category. And that post set category I will also denote as K, just to abuse the notation more. And basically, that post set category will have, you have a map, so, so the objects are simplices. And then you have you have a map when you have an inclusion. So, Hom of sigma comma tau would be either empty, well, let's say the size of it. So the number of elements in that map, it would either be empty or this would be else. And it would be of size 1. There's a unique map if sigma is a subset of tau. Okay, so you can just write an example of that. So if you have 1, 2, 3 here, if this is the simplicial complex, then you're going to have, a category that looks like this. This would be like 1, 2, 2, 1, and 3. So that would be 4. So that would be 4 objects and 2 non-trivial maps. Of course, you have the identity maps of the objects. You have the identity maps of the objects, and so that would be 2 non-identity maps. Okay, but then you also have to add the empty set that maps into everything. So that would be 4 plus 1 objects and 2 plus 4 non-identity maps. Okay, so that's a category, the post set category. Okay, right, and of course you have this map here. So for example, this morphism here between 1 and 1, 2, you have that morphism. That's since 1 is a subset of 1, 2. So it's just inclusion of subsets, and that gives you the morphisms. Okay, so we're interested in, so we want to describe the polyhedral product as a colimit of a functor out of this category K. So we can consider functors out of K. So again, we have, so we can consider, so again, we had, if you recall, we have a bunch of pairs. There's some pairs of spaces. This is just like in Martin's talk. So, I is an element of M. And of course, M is just, the things from 1 to M. Those numbers. Okay, so we have pairs of spaces, and generally we want them to be nice pairs for things to work out, like, CW complexes, and then it should be a relative CW complex, AI inside of X. So you need some conditions on the spaces. You can't do it. You could do the construction for any spaces, but for nice properties, you need conditions on the spaces. Okay, but then you could have, out of that, you could get what you could call XA underline upper blank. So this is the notation that Martin wrote for the list of spaces. And generally, I'll be slightly sloppy and sometimes not write the underline. Okay, right, so especially if all of the xi are the same. If all of these pairs are XA. Okay, so you have this functor here, which would be a functor from K into spaces. And it just sends sigma will map to this thing, which would be like Martin wrote. So that would be like the product over I, an element of M, of yi, where yi, right, it depends on, this depends on sigma. Here there's no dependence on sigma. This is a subthing of just this product of some product here, but the dependence on sigma is on the yi. So yi is either xi or ai, depending on if I is in sigma. So it's xi if I is an element of sigma, and ai if I is not an element of sigma. And this is exactly the definition that Martin gave for that last lecture. Okay, and then the polyhedral product, as Martin defined. The polyhedral product. The polyhedral product is defined to be, if you have now xa upper k, is just going to be the union sigma an element of k of x comma a upper sigma, and that's as a product, as a subthing of, well, if all of the spaces are the same, normally it would be a subthing of like x1 cross dot 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 cross xm. It's a subthing of the product of the x's, and the a's, of course, it's a pair of spaces, so ai sits inside of xi as a pair of spaces. Okay, so this is the definition that Martin gave in the last lecture. This is the polyhedral product, but it turns out that this is equal to the colimit of sigma, an element of k, xa sigma. Okay, so you can consider it really as the colimit of the functor that I described there, instead of as the union. Okay, so this equality requires some minor topological restrictions, but certainly it's okay when we have pairs of CW complexes, and A is a CW complex. Yeah, so obviously each one of the XA sigma include into here, and they include in a compatible way. So that will imply that certainly independent of X and A, independent of any topological conditions, that you will get a map from the colimit here to the union. And then under slightly mild conditions, that'll be a homeomorphism. Okay, now the more important thing for computing cohomology is that this colimit is actually a homotopy colimit. Now, I'm not really going to talk about that, but I'm just going to say, this is more like a comment, that yeah, so if, again, if the pairs are nice, like relative CW complexes, you get that this colimit is actually a homotopy colimit. Okay. And the one case we were interested in was ZK, which is D2 S1 upper K. That's one of the cases. And then the other case was this Davis-Yanuszkiewicz space, which is CP infinity, comma point upper K. Both of these are spaces that Martin mentioned. And this one, yeah, this is like the MAC, or moment angle complex, MAC. And DJK is the Davis-Yanuszkiewicz space. And following Martin's good example, I won't attempt to write down the names and spell them. Okay, right, so the idea is when you have this procedure, you can build up, when you think of it as a colimit, you can build up the space one simplex at a time. You can build up the space one simplex at a time, and that's what we're going to be taking advantage of in the proofs that we're going to be doing. So this is a proposition. suppose that we have, we have a simplex, but it's just a subset of M. And let's say its boundary, suppose that its boundary, so I'm thinking of this as a simplicial complex, so it's all subsets of M, and suppose that the boundary of it, which means all the subsets except for the full thing M, all of the subsets except for the full thing M, let's say that that is a subsimplicial complex of K. So every simplex in this boundary has to be a simplex in K. Okay, so if you have that assumption, but you also have that sigma is not in K. So in other words, you can add that to K. Okay, so then what you get is you get that there's a push out. There exists a push out, which is you can kind of glue that one simplex in. So you have, Martin talked about functoriality. Because this is a subsimplicial complex of this, you get the inclusion of the corresponding polyhedral products. And then you can also include this into X comma A upper sigma, and then you can include this into X comma A K union sigma. Okay, so this is the key push out that we're going to be using over and over again in the talk. And this is a push out, but it's also actually a homotopy push out. And so because it's a homotopy push out, you can use Meyer-Vietoris. You have a Meyer-Vietoris sequence, okay? So you have a Meyer-Vietoris sequence. And of course, for it to be a homotopy push out, you need some conditions like relative CW complex. Okay, so at this point, this is kind of the key proposition that we're going to be using. So are there any questions at this point? Comments? No? Okay, so let's go on. So you get okay, so now I'm going to talk about what Martin mentioned but didn't define, which is the face ring. That's going to turn out to be the cohomology algebra of the Davis-Januszkiewicz space. So this is the face or Stanley-Reisner ring, if you wish. Let's see, I think I'll keep this and eliminate this. I'll eliminate this. So the next thing is the face ring of K. Face ring, which is SRK, so the S I'm using, it's kind of referring to both the face ring or the Stanley-Reisner ring, sometimes it's called. Again, K is a simplicial complex, and let's say you write sigma is, I'm going to write a subset of M, but I'm going to write out all the elements that are in it. So you have some sequence of elements, and that would be a subset of M. So this is kind of like this is potentially a simplex in K. It may or may not be a simplex in K, okay? But what is IK? So I'm going to define, so this is IK. This is a subset of the polynomial ring Z V1 up to Vm, right? So this is the M, so K is a simplicial complex on 1 to M. This corresponds to all the vertices of K, okay? All the vertices of K. And I'm going to define an ideal which sits inside this polynomial ring which is generated by the vertices. Well, what is it? It is generated by things of this form, essentially. So you product these out. You get Vi1 times, Vi2, Vis. Okay, so this is a monomial. It's the product of the generators which correspond to this subset. Okay, so that's an element of the, that's an element of this ring, the product of those things. And what you do is you take the ideal generated by that, but you take the ideal generated by that for sigma not in K. You take it for sigma not in K, and such sigma are called missing faces or missing simplexes. So sigma is missing simplex. So it's a simplex that is not in K. You take that quotient, and then you take the Stanley-Reisner ring will be the Stanley-Reisner ring will be the quotient ring, or the face ring, SRK, will be this polynomial algebra, V1 up to Vm, M, all the vertices, modulo this ideal Ik, where K, of course, depends on the simplicial complex and is generated by the missing faces. So if you take this, for example, this simplicial complex, you would get Z, V1, V2, V3, the polynomial algebra on the simplices, and then you would quotient out by the missing simplices, which would be V1, V3, and V1, V2, V3. Okay, that's formally following in the definition, but you don't need this one, obviously. So this is not a minimal generating set for the ideal. Now, it turns out that this is isomorphic to, this is something you can check by induction and basically by that diagram there, which I won't prove, but you can check that that is the limit, sigma an element of K, of the things corresponding to a simplex. So you would have ZVI, where I is an element of sigma. Okay. So now you can take, the polynomial algebra is generated by the particular simplex, right? So this would be a polynomial algebra generated by the elements of the simplex, and you can take the limit over all of those, and that's going to be isomorphic to the Stanley-Reisner ring. And you can prove that by induction essentially with a diagram like that, right? By adding one simplex at a time. Okay. Right, so the theorem is actually that the Davis-Januszkiewicz space, its cohomology is SRK. Yeah, I'll leave this. This is the most important. This is the most important thing, so I'll leave that. Yes. I can't read the time. Anyways, yeah, there's time there. Okay, so the theorem is that you can compute and the cohomology of djk. Of course, I'm always using z coefficients, though I might not write the z, that is isomorphic to SRK. And of course, that isomorphism is better than just an isomorphism. It's a natural with respect to inclusions of simplicial complexes and so on. Okay, and so as an example of that, and kind of how, let's look at this picture here. If we have like, we can take empty set, goes to 1, goes to 2, goes to 1, 2. Okay, so that would be an example of this, right? Where sigma, say, is d sigma here, sigma is 1, and then d sigma, you have to take that away, so it would just be the empty set. Simplicial complex which only contains the empty set. And these would be things on 1, 2, right? Yes. Yes, please.
Does the inductive proof give you the ring structure?
Yes. Yeah, so this is, yeah, oh, sorry, this is as rings. Yes, yes, it does, yeah. Thanks, it's good. Okay, so when you do that, what do you get? So how do you, when you take, if I'm going to apply, this is kind of the input to that diagram, but now we want the output, which looks like that. So the output of that would be like, we would have CP infinity, comma point, upper empty set maps to CP infinity, comma, just one vertex, the vertex 1, comma point, and then the vertex 1. And then you would have, so what is that equal to? Right, so what you do is, yeah, so it's empty set, so there's nothing in there, so you always take point cross point. In this case, there's 1 in there, so in the first coordinate, you would take CP infinity, and then in this is a simplex, right? It's the simplex which only contains 1. And so in the first coordinate, you take 1, so it would be in there, so you get CP infinity. And then in the second coordinate, well, 2 is not in there, so therefore you'd take a point. And then similarly here for 2, if you put this, you could put, I'm drawing this diagram essentially. You could draw, you could have x comma a, so that'd be C infinity comma point, upper 2. And then it would be the same thing as 1, except you'd have point cross CP infinity. Okay, and so you get that push out or that homotopy push out, and then this is something we know what that is, that's just the wedge. Okay, so this is, when we take the push out here, when we take the push out, we get CP infinity wedge CP infinity. And then let's compare that to the theorem. So what should it be? I think I can erase this. What should it be? What we have is, we have H star of CP infinity wedge CP infinity. That's going to actually be isomorphic to Z V1 V2, and then mod, well, it's mod the products. Any product is dead V1 V2, and that's in fact the one missing simplex. The one missing simplex was 1, 2, so we get that it agrees with the theorem so far. So that's good, that's encouraging. It would be bad if it disagreed with the theorem. That would be a problem. Okay, so let's just do one more example of a specific construction like this, and it will be something that, yes, please, Gabby. Oh, thank you. Well, I guess that's true. I should write that down. SRK is this, yeah, and the degrees, thank you. Degree of VI is equal to 2. Yes, thank you. Okay, so let's just do one more example. Where we're going to do this kind of, gluing it together construction. The next example would be this. Okay, so we're going to do H upper star of DJ of 1, 2, 3. 1, 2, 3. So this is what I mean here is the boundary of delta 2, or in my notation that I was using, that would be the boundary of 3. So it's all subsets of 1, 2, 3 except for 3 itself, right? So that's a boundary there. And then the corresponding picture before you take, moment angle complexes is, well, you can start with, you can add, we have 2, 3, maps to 2, 3. That maps to 1, 2, 3, and then that maps to the thing here, which is 1, 2, 3, right? So this is like this here is the D sigma, that's sigma, this is K, and that's K union sigma. Okay, and then you can take DJ, or you can apply to this, well, you could call it DJ blank, or you could call it, you can apply DJ blank, or you could call that CP infinity, comma point blank. You can kind of apply those as functors. And then what diagram will you get? What you'll get is, well, we already did this one. That's just going to be CP infinity, wedge CP infinity, and then that would map into, here you have there's no missing faces at all, so it's just going to be the product of the generator, so that would be CP infinity cross CP infinity. Right, because there's no, because it has, that's what it is, that one. And then you would have this one would be DJ of whatever that is. I'm not writing out what that is. And then you would have dj of the thing we're interested in. And this here is a homotopy pushout. And so because it's a homotopy pushout, next thing we do is we apply H star to that, and you'll get a Meyer-Vietoris sequence. Okay, so I'm going to apply H upper star with Z coefficients, and we get a Meyer-Vietoris sequence. We get a Meyer-Vietoris sequence. Okay, that's good. I get Meyer-Vietoris. Meyer-Vietoris, which will look like this. It will look like, well, of course, the arrows are reversed, and the Meyer-Vietoris sequence will look like Z. Well, I guess the pushout, before we do Meyer-Vietoris, we get a pushout which is, which looks like this. Z V2 V3 modulo V2 V3, and then the arrows get in the other directions. That would be Z V2 V3, corresponding to the product of CP infinities. And then this one would be Z V1 V2 V3. We already did this example. You mod out by V2 V3. You don't have to mod out by V1 V2 V3 because it's already in this ideal. And then here you would get basically question mark. You would get H upper star of dj of dj of 1, 2, 3. Okay, and then you can apply Meyer-Vietoris. And the key point here to applying Meyer-Vietoris, the important thing, and this is the same proof that you would do, this is essentially adding a one simplex, right? So to say that this is isomorphic to this is essentially induction, right? By the induction step, and then the next stage we're adding one more simplex and we want to prove it in that case. And the key step here that will work in all of these cases is that all of the cases where you have the simplex, the boundary of the simplex to the simplex, this map is always going to be surjective. Okay, so this is surjective. So what is the Meyer-Vietoris? Because of that, what is the Meyer-Vietoris? So the Meyer-Vietoris sequence becomes a short exact sequence. Okay, so we get 0. So Meyer-Vietoris becomes 0, goes to Z V2 V3 modulo V2 V3. Right, so that's the corner, and then the direct sum of those two, that's Z V2 V3. Direct sum, well, Z of V1 V2 V3 modulo V2 V3. Oh, was it modulo V2 V3? Yeah, modulo V2 V3. And then you have, well, then you're going to have like the kernel of phi, and 0. So you get a short exact sequence. Again, there's no connecting homomorphism since the map is surjective. That's the key thing, okay? So this is 0 since map is surjective, since the map is surjective. That's the key step. So then you have to compute the kernel of phi. So the kernel of phi, the kernel of phi by Meyer-Vietoris, that will be isomorphic to H star of dj 1, 2, 3. And then it'll turn out, this is like a computation, which I won't do. You can compute that that is isomorphic to what you would expect, which is V1, V2, V3. Here you're only missing the top face. Okay, so that would just be V1, V2, V3, the ideal V1, V2, V3, which corresponds to the top face that's missing. Okay, and yeah, actually, I mean, I could say a bit more. That's actually a pullback of graded algebras, and this does include the algebra structure. Okay, so yeah, so you can compute that. And yeah, the last step I didn't do, that's a computation, which you can do in various ways. Okay, so that completes approximately the first half of what I wanted to say. So this technique, yeah, I'll erase this. So we're still going to be using that push out. Yes, please. Well, basically, I mean, sigma is not an element of K, but then, oh, okay, right, yes. I should have called it maybe K primed or something like that instead of K. It's like you start with K and you add one more simplex. Or if you want, you could call this K and call that K take away sigma. Maybe I'm mixing up the notation because I'm calling that, the empty triangle K, but that's really K union sigma, right? So this picture here, so we had D sigma sigma, this was K, and this was K union sigma. Does that answer your question? Yeah, it's just notation. Thanks. Right, so I was erasing this. Right, so now, I was just going to say, are there any other questions actually? Yes, please. No, this shows the algebra structure. I mean, okay, so actually these are, I guess, okay, so these are, yeah, so you have to be slightly careful there, but this is a sub thing, and actually, okay, maybe you need something else. You have to say probably, you have to keep, when you do all these constructions, you have to keep track of all the compatibilities. So this thing is a sub thing of DJ 1, 2, 3 with everything filled in. Okay, and then, there's going to be a map from Z of V1, V2, V3, which maps in here, and that'll be an algebra map. And then, it's just, then you just have to compute the kernel, and then that'll imply that this is the algebra structure holds as well. Yeah, so you have to be careful with the compatibilities. Yeah, so probably you need a little bit more, yes. Yeah. I mean, alternatively, you can think of that as a pullback of algebras. But yeah, you have to. Yeah. Okay, so actually this proof will work anytime you have x comma point computing the cohomology of this as long as x is, say, torsion free. The homology of x is torsion free, the exact same proof will work. Yes?
I'm curious if this inductive proof is why we want, after when we have pure symmetrical complexes, we want to have like the shallow.
Okay, well, that's a complicated question, which I'll defer to, maybe Stephen will talk about that in his lecture. I'll just say some point at somebody, no, I don't even know what a shelling is actually. But I mean, yeah, so that is kind of, all of these, yeah, so in the background is we want to, so this is a general, maybe I can answer that in this way. Part of the story of polyhedral products and moment angle complexes is that you want to understand how the properties of the simplicial complex affect the properties of the moment angle complex. So shellability is some kind of property of the simplicial complex. And if you have that property, it may give you some properties of the moment angle complex. And actually, this is something Stephen will talk about. Yes, okay, an example of that. But that's a general philosophy. What kind of things, what kind of properties of simplicial complexes can you exhibit in, say, the cohomology or in splitting results and so on? So that's a general philosophy, yeah. But yeah, as I was saying, this proof generalizes to something of this case as long as the cohomology of X is torsion free. But it doesn't work for ZK, right? It doesn't work for ZK because Meyer-Vietoris doesn't give enough information because you don't have surjectivity on homology there. You lose that for the moment angle complex, so you have to use a different approach. And so for ZK, we have to work at the chain level. I believe co-chain level. I believe that generally you can kind of sometimes get away with not working at the co-chain level, but working at the co-chain level and maintaining the construction at the level of co-chains generally always gives you more information. So it's a good thing to do in general, to maintain things at the level of the co-chains. Okay, so let's see here. Okay, so here's the theorem that we're going to show, which is that, well, we're going to show that when you take the moment angle complex, so remember that's just D2S1 upper K, another notation for that, that is, okay, now I'm going to explain this notation in a second. Some people may be familiar with it, but it is quasi-isomorphic to U1 up to UM, and then tensor, actually the Stanley-Reisner ring with some differential. Okay, now I have to explain a few things in here. This part here, sorry, including the everything here. This is exterior algebra. Okay, we know what this is. That's the Stanley-Reisner, or the face ring. So we know that. And then we just have to say what D is. D is, you just have D of U1, D of UI equals VI. Okay, that's the differential. Okay, so that completely describes what this is. I believe I have a couple of things to mention, which is the degrees and that twiddly symbol. Yes? The BIs appear in ZK. I defined it right there. It's still up there. Oh, ZK, okay, sorry. I'm very sorry. This is really S, I should use the same notation, which is SRK. ZK is an alternative notation. Any other questions? Thanks, Tony. Right, so everything has been described there. There's a little bit more information that we want. We want to say that this is isomorphic to the same thing, but modulo, it's quasi-isomorphic to the same thing, which is VI, you can mod out by VI squared UI VI. The reason you can mod out by the reason you have this equivalence is because, yeah, this is an acyclic ideal. So you can quotient out by an acyclic ideal and you will maintain the same kind of homotopy type of DGAs. So I'll just explain this and the degrees. So here we use bidegrees, which are actually incredibly useful in applications. So I will write things as bidegrees. So the degree of UI is equal to -1, 2, and the degree of VI is equal to 0, 2. Okay, so they actually have bidegrees. If you want to get the normal cohomological degree, you just add the degrees together. So this would be of degree 1 and this would be of degree 2. What else? Oh yeah, so what does this mean? So that symbol essentially means, so I can say that A is, okay, I would say is quasi-isomorphic to, is equivalent, is weakly equivalent or quasi-isomorphic to. That's a notation which is quasi-isomorphic to if there exists a C like this, we have maps like this, where these are, everything is in the category of DGAs. So this is a DGA map that is an ISO after taking cohomology. After taking cohomology. So once you take cohomology, it'll be an isomorphism. Okay, so in particular, okay, that's kind of like, I mean, there's some stuff under that I haven't really talked about so much, but anyway, so that's the basic idea. Well, one thing is normally people would think of these as connected by a sequence of them, but you can always reduce it to a sequence of length 2 like this, okay? The other thing is, for example, what does that say? That says, for example, when you compute if you want to compute the homology or the cohomology of the moment angle complex, you just have to take the cohomology of this model. And this model is much smaller. I mean, the cohomology of this, if you take the cochains on this, it's some huge, gigantic thing. And this is reasonably small. And this, once you quotient out by VI, UI, VI, it's much smaller. It's finite, finite dimensional, finite as a Z module. finitely generated as a Z module. So generally speaking, so this makes it much smaller and much computable. But beyond that, because it's a quasi-isomorphism, you can compute all other kinds of invariants such as Massey products and so on using this model. Compute the Massey products here. Okay, so that's why it's useful. And this is kind of, yeah, just a quick outline of that idea. Okay, so and again, so are there any questions? 13. Okay, well, I guess I'm slightly running out of time, but okay. Okay, so again, how do you prove this? You can prove this, there's various ways of, I'm going to follow Franz's proof of this. So Franz's proof of this essentially uses, again, induction. So I have some pictures that I won't be able to include. You can always ask me about them later, which is the proof of the following proposition, which is not that difficult in this case. So the proposition would be, what do we want to say? We want to say that if you take, this is a general thing for moment angle complexes. If you take the colimit of sigma an element of k of x comma a upper sigma, so we saw that this is just x comma a upper k. That's what this thing is. You can take that out of the C star. There's going to be a map here into, each one of them will have a map into C star of x comma a upper sigma, because there's like a restriction. There's a restriction map. So you get a map into here when you take C upper star. You get a map into here, and actually then you can take the limit of these. And the proposition is that that's not an isomorphism, but that's a quasi-isomorphism. Okay, and you can prove that again by induction, and unfortunately I have a proof, more explicit proof written down here that I don't have time to do. So this should be true. The thing is that this should be true. Okay, so first of all, I'll just make a few comments. Really, we're taking homotopy colimit here, and we're taking homotopy limit here, and this kind of statement works for much more general diagrams. Or limits and colimits over much more general categories. But the thing is that when you take a simplicial complex, the proof of it becomes very easy because you can use this inductive proof. Okay, and it's also easy to recognize what are homotopy colimits and what are homotopy limits in this case. Easier than in the general case. Okay, and there's a proof of this, but I'm sorry, I don't have time to write it down. I mean, other than in my notes. Okay, so what's next? So the next thing is, and this is kind of, right. So the next thing is, what you want to do is you want to take this limit. Okay, so the thing is that you want to take this limit, but this is already, so in the theorem we have some small things, right? They're finite generated Z modules, but this C star is something complicated. So we have to do some kind of replacement. So this is like models. Okay, and so the theorem is if, so this is like a theorem or proposition, say. If, so let's say we have a diagram of DGA, which looks like this. So first we have C star of X and C star of A, and then we want to compare that to some other DGAs which are B, E, and then you have in between, you have something that sits in between, like this. And then you need some other conditions that all of the horizontal maps are weak equivalences. Horizontal maps weak equivalences. And the vertical maps should be surjections. That's so that our limits will turn out to be homotopy limits. Vertical maps are surjections. Okay, then we can essentially, so these ones are all surjections, and the horizontal maps are quasi-isomorphisms. Then essentially we can replace these things by things constructed out of B and E. Okay, I'm ignoring the fact, as I said, now all of the X's and A's are the same. I don't have Xi, AI, but it would be the same result in that case. Okay, so what's the result is that you can replace these things. So then you will have that the limit, you'll have that the limit of sigma an element of K of tensor over I an element of sigma. When you're in sigma, you take the B, which corresponds to the X, and then tensor sigma naught in I not in sigma of the E's. And you can take the limit of that, which will be much smaller, and that is quasi-isomorphic to C star of X, comma A, K. Okay, so you can replace this possibly very big thing with this somewhat smaller thing, because B and E could be very small. Okay, now how you would prove that is basically this is quasi-isomorphic using that diagram to the tensor product of I, an element of sigma of C star of X, tensor I not an element of sigma of C star of A. These are quasi-isomorphic. That's just generally, that's kind of general nonsense or whatever. I mean, of homotopy limits. Yes, please.
Are these chains or cochains?
These are cochains. Everything is cochains here. Oh, sorry. Yes, you're right. Thank you. Yeah, this is cochains. Yeah, it's all cochains. And then, of course, this is quasi-isomorphic to, C upper star X, comma A. So this is basically, there's going to be a map. The map goes in this direction, I think. The map goes, I forget which direction. This is basically Alexander-Whitney. This is essentially the Alexander-Whitney map, upper sigma. And then this is just general kind of things about homotopy limits. That uses Alexander-Whitney. Okay, so, okay, I have 2 more pages. Okay, so the corollary of this, so are there any questions? So basically the idea, oh no, I have one more, yeah. Right, so that's just, you can replace basically this complicated model with a simpler model. And here I've written, you have to switch the factor. I've written them not in correct order, right? Because sigma, M is an ordered set, so you have to switch these around and put it in the right order. Okay, so this is the statement, and then this is an outline of the proof of that statement. Okay, this is an outline of the proof, and this is the statement, so let's say proof. Proof is this part. And a corollary of that is that if X is formal, and torsion free, and H, so that means that i.e. H upper star of X is quasi-isomorphic to C upper star of X, and torsion free, and H upper star of X is torsion free, then this one we knew how to compute the cohomology of, X A upper K is formal. Okay, so that's a corollary of this. Okay, so the next thing is, how do you apply this situation, or how do you do this situation, and how do you apply it to moment angle complexes? So this is, and I'm going to follow Franz's approach to this. So basically, I want to construct a diagram. The idea is to construct a diagram like this, where we have D2S1, and we have some simple B and E here. Okay, that's the idea. So what Franz did was he went C star. So he constructed a shorter map. So he made this is you could consider as an this one could be an equality in his situation, but you can do it more generally. It's upper star. He starts with chains, but then the result for cochains is that you get some map here. This would be like R. R was the algebra. Oh, did I say what that algebra was? No. Yeah. No. Well, this would be R of a point, which is basically just, this is isomorphic to Z1 UV. This is like, if you have D2, it's like a moment angle complex with just one thing. So if you look at that algebra, it looks like this. It's Z like this as a module. And then you have products. Basically, all products are 0. Well, 1 times x is equal to x, but the other products, which would be u times, well, u squared equals v squared equals uv equals 0. So it has all other products are 0. And then you could go down to R of the empty set, and that's isomorphic to just you have the u there. Okay, and these are quasi-isomorphisms. And these, of course, are surjections. And, you know, Franz constructs a diagram. I mean, he doesn't maybe phrase it this way, but Franz constructs a diagram like that. And then we can apply this proposition to that. Okay, and then you can apply the proposition. And, yeah. And then again, by induction. So the idea is apply the proposition. Apply proposition that I just erased. Apply proposition. Basically, it's this prop. That's what I'm applying. So apply plus. Apply that, which was the proposition, and induction. To show that, well, first of all, we'll show that, you know, that the limit that C star of ZK, which is that thing there, is quasi-isomorphic to this limit, which is this limit here, the limit sigma element of K of that exactly there, tensor of R like point, tensor R empty set, exactly as it's written there, the tensor product of these things, where I is an element of sigma, I is not an element of sigma. So that's the plus implies this, that's the proposition, and then you can show that this is isomorphic to RK. So RK was that thing, was the Kazul algebra, so RK, just to write that out, I don't know if I wrote it out, but that was like lambda U1 V UM tensor SRK with a differential, but it's the thing that after you mod out by UI, VI, and VI squared. Right, so this part is induction. Induction by essentially adding one simplex at a time. Okay, and this part is the other proposition. Okay, so that's how you can show that C star of ZK is quasi-isomorphic to RK, which is this quotient, this small quotient algebra. Okay, so that's an important algebra. Right. So, right, that was also observed by Boxhaber and Panoff previously. Okay, so yeah, so then induction is that, and that's basically most of what I wanted to say. I just wanted to say a couple more things. Oh, also, yeah, I wanted to say a couple more things. So this is one approach to this problem, is as Franz does it. There's another approach where you could find some, you know, as in the diagram I had before, you could find some intermediate model. And you should be able to do this approach, finding the intermediate model should generalize this result to being able to compute some similar chain model as of something of the form Cx, comma x, if x is in the stable range. So if x is, you know, the dimension is low enough with respect to is less than twice the connectivity. You should be able to get a similar model using an intermediate model here, just using obstruction theory. So there should be a proof like that. So that's a problem. The problem set is later, but that would be a problem to look at. Okay, and then I just wanted to mention a couple of other things. Just one or two other things, because Tony, yes?
That would involve the code changes on the x itself and that comment you made about the generalization.
Yes?
The sinvex comma x, you made some comment just a few seconds ago. It would involve the code changes on the space x itself, but it would be involved in that model.
Yes, but the thing is that the cochains on X, basically because it's in the stable range, you don't have any products. So you're always going to have, because you don't have any products, you're always going to have, you're going to have something which is basically the cohomology of X. Okay, and probably you need torsion free as well. Okay, but then you're going to have the cohomology of X goes into C star of X. This is going to be a quasi-isomorphism actually of DGAs. Right, and then you have to do something with the C of X, get some extensions, but that would be like you could maybe use some kind of obstruction theory for that, just because something like obstruction theory.
You're not suggesting like using kind of a complex built out of the cochains on X even if it's not in a stable ring.
No, I mean, that is basically what this says in some sense, right? So that you don't really know what that is because the cochains on X are some unimaginably huge thing. Right, so that would be kind of a more general problem, let's say, is look for nice, models of, just A into X. If you have nice models of A into X, using this you can get nice models of the moment angle, of the polyhedral product. So that's a more general problem. This is a very specific case of that, where I think the path is not obstructed. Yeah.
T1S naught carries the information together with the homology of X.
Yeah, I mean, so maybe I'll say something. This is right. I mean, you're talking about the cohomology structure or the chains. Right. So yeah, for the cohomology structure, and I think Martin's going to talk about this, and I just wanted to, because I made Martin a promise that I don't want to lie about. So I just have to. Sorry, I'm over by 2 minutes, but I need like 1 more minute, so I'm not lying to Martin. Okay, the way I'm not lying to Martin is that, okay, so there's another way. So this is kind of one approach to computing the cohomology of a moment angle complex, but there's another way, which is that if you look at H star of ZK, and this is also foreshadowing for both Martin's and Stephen's talks, I believe. So that there's the Hochster decomposition, which says that this is so now I'm just looking at the homology of ZK, not the cohomology. So this is the direct sum over all I, a subset of M, of the reduced homology of Ki, where Ki is the induced subcomplex.
I didn't mean to make you intrude on their talk.
Well, no. I had a specific request from Martin, which I'm trying to fulfill right now, which is that there's an isomorphism like this. So this is the induced subcomplex. So you take the simplicial complex and you restrict it to a subset of the vertices and take the simplices that are in that subset. That would be the reduced subcomplex. This is called the Hochster decomposition. And I believe Martin is going to show that give a topological version of this, that this is true topologically after a suspension. And then Stephen is going to improve that by saying, you don't even have to suspend if K is of a nice form. So that's an example of the kind of thing I was talking about where, you're getting information about K somehow. How is K, the properties of the simplicial complex, related to the moment angle complex? And Stephen will give an example of that. Okay, thank you.